In the first part of this example, we're just trying to figure out the mass of CHCl3 in atomic mass units. Well, that's not so bad. We can get the mass of each individual atom in the molecule by just looking at the periodic chart. Well, this molecule has carbon, hydrogen, and chlorine, so we have to look at those three entries on the periodic chart. Carbon's entry tells us that a carbon atom has a mass of 12.0 atomic mass units. That's what that bottom number means. It gives us the mass of the atom in atomic mass units. Well, this molecule has a carbon atom, but it also has a hydrogen atom. Hydrogen's entry on the periodic chart tells us that a hydrogen atom has a mass of 1.01 AMUs. Well, the mass of the molecule is going to involve the mass of both the carbon and the hydrogen, so I'll add those two masses together. So far I've got 12.0 AMUs for the carbon and 1.01 AMUs for the hydrogen. Well, the only other atom in the molecule is chlorine. Chlorine's entry tells us that chlorine has a mass of 35.5 atomic mass units. However, there are 3 chlorine atoms in this molecule. So I have to take that 35.5 and multiply by 3 because I have 3 chlorine atoms. So the mass of CHCl3 is the mass of 1 carbon, 1 hydrogen, and 3 chlorines. When we work this out on the calculator, we get 119.51 AMUs. However, that's too many significant figures. Remember, we're really adding here. Even though we multiply by 3, that 3 is exact. It's not 2.9 or 3.1. It's exactly 3 because you can only have 2, 3, or 4 chlorine atoms. You can't have something in between. So in the end, what we're really doing is taking 12.0 plus 1.01 plus 35.5 plus 35.5 plus 35.5. So what we're really doing here is adding. Well, when we add, we look at decimal place, and we report our answer to the same decimal place as the least precise number in the problem. The mass of 12.0 and the mass of 35.5 each go out to the tenths place. So my answer can only go out to the tenths place. So the real mass is 119.5 AMUs. Alright, so that wasn't so bad. Now let's move on to the second part of the example. This time I want to find the mass of another molecule, but I want to find it in grams, not atomic mass units. Well, this molecule contains silicon atoms, fluorine atoms, and oxygen atoms. So we have to look at their entries on the periodic chart. A silicon atom has a mass of 28.1 AMUs. We've got 6 of them, so we have to multiply by 6. A fluorine atom has a mass of 19.0 AMUs. We got 12 of those, so we have to multiply that by 12. An oxygen atom has a mass of 16.0 AMUs, and we've got 6 of those, so we have to multiply by 6. When we work all that out, we get 492.6 AMUs. That's the proper significant figures because each mass goes out to tenths place, so our answer can go out to the tenths place. However, that's not the answer. The mean guy who wrote this problem doesn't want the answer in atomic mass units. He wants the answer in grams. So we've got to convert from atomic mass units to grams. That's not so bad, though, because we have a conversion relationship. According to the book, 1.00 AMUs equals 1.66 times 10 to the minus 24 grams. So we can use that to convert. We take our original measurement and put it over 1. Then we multiply by the conversion relationship. Since I want AMUs to cancel, that needs to go on the bottom, so 1.00 AMUs go on the bottom, and 1.66 times 10 to the minus 24 grams goes on top. When I multiply these two fractions, AMUs cancel, as they should, and I end up getting 8.18 times 10 to the minus 22 grams. Since 1.66 has only 3 significant figures, I have to round my answer to 3 significant figures, so that's why the final answer is 8.18 times 10 to the minus 22 grams.